Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow. Let's keep leveling up together.
Today, we're doing a deep dive that should, I think, really change how you approach some of the biggest decisions you have to make as an engineer.
Yeah, we're talking about those high-stakes choices.
Exactly. The ones that determine safety, cost, the actual lifespan of these huge multi-million-pound assets. The mission here is to move all of that away from, instinct or just, this is how we've always done it.
And anchor it in something solid.
Anchor it firmly in verifiable, defensible numbers.
That's the real challenge, isn't it? Bridging that gap between a technically brilliant idea and, well, corporate accountability.
Yeah.
The core question we're really trying to answer today is, how do I prove that one design is numerically safer or more reliable or just flat out more cost-effective than another?
And not just for day one.
Right, not just for startup, but across the entire, multi-decade life of the thing.
We've put together a framework for that kind of engineering accountability. We're going to walk through 4 critical pillars.
Okay, what do we got?
First, risk quantification. This is where we justify safety decisions with hard data, probabilities, consequences, the whole 9 yards.
Getting past the hand-waving.
Precisely. Then we'll get into post-failure investigations. This is about learning something real from a defect report, not just patching the symptom.
So what actually went wrong?
What actually went wrong and how we stop it. Third, we'll tackle human error integration. This is the uncomfortable one, the truth that, human performance often dominates how reliable a modern system is.
It's not just about the hardware anymore.
It's rarely just about the hardware. And finally, we'll bring it all home with designing for the full life cycle. This is where we show why the cheapest option up front is often the most expensive one you can possibly choose.
Okay, this is a huge topic. Let's get into it, starting with that bedrock principle, risk quantification for decision-making. We need to take that vague fear of what if and turn it into something management can actually act on.
Right, into cold, hard math.
Exactly.
The whole foundation for this rests on a really precise technical definition of risk. Risk isn't just, a hazard existing.
It's more than that.
It's explicitly 2 measurable things that you have to look at together. First, the frequency or the probability of something bad happening.
Okay, so how often?
How often? And second, the measurable scale of the consequence that results from it.
So if I'm designing a pipeline, it's not enough to say the pipe might break.
No, that's useless.
I have to say how likely it is to break and then quantify the outcome, the damage, the environmental harm, or, the loss of life.
Precisely. And that's the whole point of a Quantified Risk Assessment, or QRA. It's the structured process of taking those 2 things, frequency and consequence, and actually putting numbers on them.
Which lets you compare things.
It lets you compare different risks, different designs, different safety measures, apples to apples.
So walk us through that classic process plant example. It really shows how this works in practice.
Sure. So imagine you're assessing a big process plant. It's near a town, and it handles some pretty nasty materials, toxic, flammable, you name it.
High hazard.
A very high hazard situation. Your QRA, after a lot of work, might determine that the probability of a catastrophic release is, let's say, 1 in 10,000 years.
Okay. 1 in 10,000. On its own, that sounds incredibly low. Most people would hear that and think, okay, we're good.
Right. It seems acceptable because it's so rare, but then you have to bring in the other half of the equation.
The consequence.
The consequence. So your consequence analysis models the toxic plume. It factors in wind, population density, maybe time of day, and it determines that this one single event would result in 40 fatalities.
And suddenly that 1 in 10,000 year number doesn't feel so reassuring.
It's completely changed the picture. That combination, a rare event with a catastrophic outcome, now defines the whole scenario as an unacceptable risk. It doesn't matter how low the probability seems, the consequence is just too high.
This sounds like a massive undertaking. You can't just guess these numbers. You need some kind of formal, structured way to figure out what could even happen in the first place.
Oh, absolutely. It's incredibly rigorous. You start with what's called a HAZID, hazard identification.
HAZID.
This is where the whole team engineers from every discipline gets in a room and systematically identifies every single possible hazard in the design. They're asking, where's the energy? Where are the toxins? Where can things break?
And after you've identified the what, you move on to the how.
Exactly. You move to the HAZO2. the hazard and operability study. This is where you take those hazards from the HAZID and you figure out how they might actually arrive.
So not just the tank could overpressurize,
Yeah.
but the cooling water could fail, leading to a runaway reaction, leading to overpressurization.
Precisely. It uses these systematic keywords like no flow, more temperature, to force you to think through every possible deviation from the design intent. It's like a structured, creative brainstorming session for disasters.
And once you figured out the failure mechanism, the final piece is the HAZAN.
The hazard analysis, or as it's also known, consequence analysis. And this part is highly specialized. You're talking complex, modeling fluid dynamics, chemical dispersion, you name it, to predict the physical outcome.
So the HAZAN gives you the 40 fatalities number from our example.
Right, that's the output. And that number plugs directly back into your overall QRA.
Okay, so that's the consequence side of the equation. Let's flip over to the frequency side. How in the world do you predict the probability of failure for, say, a brand new system?
You rely on the established methods of reliability prediction. The workhorses here are tools like fault tree analysis, FTA, and reliability block diagrams, or RBDs.
And these tools let you build up a system's reliability from the reliability of its individual parts.
Exactly. You're using known failure rates for pumps, valves, resistors data that's often been collected over decades by industry, and you combine them logically to predict the failure rate of the whole system.
The logic of the fault tree is, I think, a real light bulb moment for a lot of engineers. Can we break down those logical gates, the A&D and the OR gates?
Yeah, the translation is key. So if your fault tree uses an A&D gate, you're modeling a system where multiple things have to fail at the same time for the top event, the big disaster, to happen.
It's redundancy.
It's the model for redundancy. It's the same as a parallel diagram in an RBD. And because simultaneous failures are way less likely, you multiply the probabilities of the individual failures together.
And when you multiply two small numbers, you get an even smaller number. So redundancy drastically cuts your failure rate.
Right, that's high-integrity design in action. Now, the flip side is the OR gate.
The OR gate.
If you use an OR gate, you're modeling a series case. Think of a simple chain. Any single link breaks, the whole chain fails.
So failure of component A or component B or component C, and you're done.
You're done. The system fails. And in that case, you're basically adding the failure rates. So the system's overall failure rate is going to be dominated by your single worst component.
So once you've run these huge, complex analyses, what's the key output? What's the thing you take to management that actually gives them strategic direction?
They need actionable intelligence, and the most powerful output for that is the list of ranked cut sets.
Ranked cut sets. Okay, what's a cut set?
A cut set is the minimal combination of component failures that are necessary to cause that top-level event. The analysis then ranks these different failure paths in order of their percentage contribution to the total system failure rate.
Ah, so it's like a Pareto analysis for failure. You're finding the 20% of failure paths that cause 80% of the risk.
You've got it. It's incredibly powerful. For example, you might analyze a fluid system and find that the failure path involving the PUMP contributes 50% of your total risk. The path with the motor contributes 40%. And literally every other possible failure path combined only accounts for the last 10%.
That's amazing. So instead of just guessing where the weak link is or spreading your budget thinly across every component,
Well, you now have data. You know with numerical certainty that improving the reliability of that pump will give you the single biggest risk reduction. It tells you exactly where to focus your money and your engineering effort. It moves the conversation from opinion, I've always had bad luck with these motors, to defensible fact.
which brings us to a really difficult area where engineering meets, I guess, public policy and ethics.
Yeah.
How do you decide what level of risk is acceptable? I mean, we know zero risk is impossible.
It is. And this is where we have to define 3 zones of risk. At the very top, you have the unacceptable risk zone. If your analysis puts you there, you have to reduce the risk. Cost is not an object.
Okay, that's clear.
Below that, you have the tolerable risk zone. And this is where the core principle of ALARP applies.
ALARP, as low as reasonably practicable. I've heard that phrase 1,000 times, but what does reasonably practicable actually mean to a working engineer?
It means that if your risk is in this tolerable zone, you still have a duty to reduce it further. You have to keep pushing it down unless the cost of the next safety improvement is grossly disproportionate to the safety benefit you'd get.
So you have to do an economic justification for not making it safer.
Precisely. You have to prove that spending, say, £1 million to get a tiny, almost immeasurable safety benefit just isn't a reasonable use of resources. But the burden of proof is on the engineer.
And engineers translate these abstract principles into actual design targets using safety integrity levels, right? SLs.
SIs are absolutely paramount in any high-hazard industry. They run from SIL1, which is the least stringent, all the way up to SIL4, the most stringent. They give you a quantitative target for the reliability of any safety system, like an emergency shutdown.
And how demanding are we talking for something like a SIL4 system?
We're talking almost unbelievable numbers. For a system that's in high demand, meaning it's always operating, SIL4 requires a dangerous failure rate of between 10 to the power of -9 and 10 to the power of -8 failures per hour.
So, a 1 in a billion chance of failure per hour. That's a level of certainty that demands absolute rigor in everything. Design, components, analysis, everything.
It does. And, you mentioned something earlier that trips a lot of people up. The difference between failures per hour, which is a rate, and probability of failure on demand, which is a dimensionless number.
Oh, I got two different metrics.
It really depends on how the system is used. For that high demand system, like the car brakes we talked about, it needs to work constantly, so we care about its failure rate.
That makes sense.
But for a low demand system, think of a fire suppression system. It might sit there doing nothing for years. We don't care about its failure rate per hour. We care about one thing: the probability it will fail on the one occasion we actually demand it to work. That's probability of failure on demand. It's unavailability.
That clarifies it perfectly.
Yeah.
Okay, let's get to the final financial justification. How do you convince the board to spend £1 million on a safety upgrade?
You have to speak their language. And that means using a metric called cost per life saved, or CPLS.
Now, this is controversial. You're putting a price on a human life.
Well, yes and no. It's controversial, but engineers use it not to set an absolute value on life, but to rank different safety projects. If you have a limited budget, it helps you decide where to spend it to get the most protective benefit.
So you're not saying a life is worth X amount. You're saying Project A saves a life for X amount, and Project B saves a life for Y amount, so we should do the more efficient one first.
Exactly. It's a ranking tool. Take the motor car braking system example.
Okay, lay out the numbers.
Let's say a braking system upgrade costs £40 per car. The manufacturer makes 2 million cars a year, and your QRA predicts this upgrade will save 500 lives annually in the UK.
Okay.
The CPLS calculation is £40 times 2 million cars divided by 500 lives saved.
So that's £80 million divided by 500, which is £160,000.
£160,000 per life saved. That number now becomes your benchmark. You can use it to justify the expenditure to management and regulators. It translates a safety measure into a concrete financial figure.
And that is a perfect transition. We've proven the safety case, we've justified the initial cost, but that's just year one. What happens over the next 20 years? This brings us right to our second pillar: post-failure investigations that actually teach something.
Right, because even the best designed systems will eventually fail. The key is turning those failures into actual knowledge.
And to do that, you first have to understand where on the reliability life cycle the failure happened. We're talking about the famous bathtub curve.
The bathtub curve is fundamental. It charts the failure rate of a component over its operating life, and it shows 3 really distinct phases.
The first phase is a high but decreasing failure rate.
That's infant mortality. These are failures that happen right at the beginning of a component's life, and they're almost always caused by manufacturing defects.
So things like bad welds, cracks, maybe just incorrect installation.
Exactly. Substandard items that were flawed from day one. The solution here isn't a design change. It's better quality control in your supply chain. Burn-in testing, better screening.
Then the curve flattens out in the middle.
That's the period of random failures. The failure rate is constant. These are the failures we assume are caused by random stress events in the environment, a power surge, a vibration that just happens to exceed the component's strength.
And this constant rate, that's what we typically call the design reliability.
That's the number you're aiming for in your initial QRA models. And since these are truly random, the best defense is redundancy.
Okay, and then as the component gets old, the failure rate starts to climb again, sharply.
That's the wear-out phase. This is predictable aging. Corrosion, fatigue, friction wear. Things are just getting old and breaking down.
And if you know a component has a wear-out life, the goal is to replace it before it hits that steep upward curve.
That's the entire basis of preventative maintenance. So understanding which of those 3 regions your failure came from is the absolute first step in any real root cause analysis. So even before we have failures, how do we systematically think through what could go wrong.
That's where you use a failure mode and effect analysis, or FMEA. It's a bottom-up process where you look at every single component in a system and ask, how can this part fail and what is the effect on the overall system if it does?
So you're tracing how a single resistor failing open could lead to a total loss of communication for the entire system.
Precisely. And there's a really important nuance here. If you just add up the failure rates of every single part, the parts count total, that number will always be higher than the failure rate for a specific system failure mode you're analyzing.
Wait, why is that? That seems counterintuitive.
Because not every component failure matters to the function you're looking at. A light bulb on a control panel might burn out, but if it doesn't trigger the emergency shutdown, it's a component failure, but it's not a system failure for that shutdown function. FMEA helps you focus only on the failures that actually have a dangerous effect. Okay, so now we have all this failure data coming in from the field. Hundreds of defect reports. How do you decide what to fix first? Where do you focus your limited resources?
You use Pareto analysis, the old 80-20 rule. And while it's useful to rank defects by how often they happen,
There's a better way.
there's a much more powerful way. You rank them by their total cost contribution.
So you focus on the most expensive problems, not just the most frequent ones.
It gives you incredible financial leverage. You might have, say, a fault in a mechanical transporter that only happened 4 times, low frequency, but each repair was so expensive that it accounted for 22% of your total failure costs for the quarter.
Meanwhile, you might have a printed board fault that happened 15 times.
Right, very frequent. But maybe each fix was cheap, so even though it happened a lot, it only made up, say, 35% of the total cost. By fixing that one printed board issue, you eliminate over 1/3 of your entire failure budget.
You get the biggest bang for your buck.
Exactly. You focus your investment where it has the greatest economic impact.
Of course, all of this analysis relies on getting good data from the field. The old saying, garbage in, garbage out, must be especially true here.
It's the absolute truth. You need incredibly detailed, specific information on your failure report forms.
What's on that essential checklist?
You need to track repair time, both active and passive. The exact fault type. Was it random? Was it induced by a person? Was it a primary failure or a secondary one? You need the nature of the fault wear out, drift, a design flaw, and you need the exact location and the environmental conditions at the time.
I imagine tracking time consistently is a huge challenge, especially for those wear-out parts.
It's a non-negotiable nightmare. You have to be totally consistent about using calendar time versus actual operating time. For a pump that only runs 8 hours a day, its wear-out life is measured in operating hours, not days on the calendar.
And this is where unique tag numbers for each component become critical.
Absolutely. The tag number is the component's birth certificate and medical history. If a valve body has been there for 5 years, but you replaced its internal diaphragm last year, the time to failure clock for the diaphragm started 1 year ago. For the valve body, it's 5 years. Without that level of tracking, your wear-out data is completely useless.
What are the common pitfalls you see that lead to companies collecting this kind of misleading data?
There are 2 big ones that corrupt data all the time. The first is recording non-failures.
Recording non-failures, how does that happen?
It happens during troubleshooting.
Yeah.
A technician is trying to find a fault, so they start swapping out parts one by one. They replace board A, still broken. They replace board B, still broken. They replace board C, and it works. The problem is, often boards A and B get logged as failures, even though they were perfectly fine.
So you're inflating the failure rates for good components.
And you're burning through your spares inventory for no reason. The second big issue is confusing a secondary failure with a primary one.
Explain that.
A primary failure, say a power supply failing, might send a huge voltage spike that fries a downstream circuit board. That fried board is a secondary failure. It's a victim. If the technician just replaces the board without finding the root cause in the power supply, it gets logged as a primary failure for the board.
And all your data now points to the wrong problem.
You end up spending a fortune trying to make a more robust circuit board when the real problem was the cheap power supply all along.
It's so clear that reliability has become less about perfect hardware and more about perfect information systems and analysis. Which brings us to the third, and maybe the most uncomfortable pillar, human error and operational risk.
Yeah, this is where it gets really complicated. The whole paradigm of system failure has shifted.
Right.
For a modern, complex system with lots of redundancy and controls, failure is no longer dominated by random hardware breaking.
It's become a system problem.
It's overwhelmingly a system problem, and it's dominated by software, by the environment, by common mode failures, and most of all by human factors.
So the weakest link isn't the steel anymore. It's the person operating the system or the person who maintained it last week.
And history proves this over and over. Major industrial disasters, they rarely happen because a single piece of equipment failed on its own.
There's always a human element.
There was always a significant human factor in the chain of events. Look at Flixborough in '74 or Piper Alpha in '88. The initial hardware failure in those cases was often manageable. It was the series of procedural mistakes, organizational failures, and human decisions that cascaded it into a catastrophe.
And the regulators have learned this lesson, right? This is mandatory now.
It is. Regulatory bodies now require that hazard assessments must specifically analyze the role of human error. It's not an option anymore. This means human reliability analysis, HRA, is a required part of a safety case for any major facility.
But that's the real challenge. How do you quantify human behavior? How do you put a number on the probability of a person making a mistake?
You use specialized HRA models. They try to estimate human error rates by looking at things like stress, training, and the complexity of the task. One of the most common and detailed methods is called HART.
HART, the Human Error Assessment and Reduction Technique. How does it work?
So HART starts by giving a task a baseline error probability based on its type. For example, a totally unfamiliar task performed at speed.
High stress.
Very high stress. That might get a baseline error probability of, say, 0.55, a 55% chance of error.
And on the other end?
A routine, highly practiced, rapid task might have a baseline probability of just 0.02, a 2% chance of error.
So that's the starting point.
Yeah.
But then you have to account for the real world, the time pressure, the confusing instructions, the poor lighting.
Right. And that's the next step. You take that base rate and you modify it using up to 38 different error-producing conditions, or EPCs.
And these EPCs each have a multiplier that increases the chance of an error.
And some of those multipliers are huge. For example, unfamiliarity with the critical situation can multiply the base error rate by a factor of 17.
17.
A shortage of time for error detection and correction has a multiplier of up to 11. Even something that sounds soft, like a low awareness of risk, can multiply the probability by 4.
So if management is rushing a critical job, they are mathematically increasing the risk of a catastrophic human error by a factor of 11.
That's the risk penalty they are choosing to pay for speed. Now, the trickiest part of HART is how the analyst applies these factors. It involves judgment.
So how do you make that judgment auditable?
The analyst has to assign a proportion of the effect for each EPC, a number between 0 and 1. So if the maximum multiplier for inexperience is 3, and the analyst judges the situation as about 40% of that worst-case inexperience, they use a formula to calculate a final factor of, say, 1.8.
So that specific level of inexperience increases the error chance by 80%, and you do this for all the relevant conditions.
Exactly. You multiply the baseline probability by all the calculated factors for all the relevant EPCs to get your final human error probability. It provides a documented quantitative trail for what is, at its heart, a judgment-based assessment.
One of the biggest fears with human error is that it can defeat all the clever redundancy you've designed in. A single mistake can take out both systems.
That's common cause failure, CCF. It's a huge organizational risk. You have 2 redundant pumps, but the technician miscalibrates the sensors on both of them in the exact same wrong way. Your redundancy is now worthless.
So how do we defend against that?
It comes down to 2 things: procedures and design. Carefully written, properly followed procedures are your best defense. They optimize the sequence of actions and prevent people from skipping critical steps.
They reduce the cognitive load on the person doing the work.
Exactly. And the second defense is designing for maintainability. The physical layout of your equipment has a fundamental impact on the likelihood of a human making a mistake while working on it.
You're talking about things like just being able to reach a bolt easily.
Yes. Engineers use a formal maintainability checklist. It asks questions like, is there adequate physical access for a person to see what they're doing? Is there room for their hands and tools? If the answer is no, the chance of error goes way up.
And things like standardizing fasteners, so you don't need a dozen special tools just to open a panel.
Or needing supplementary materials. If a routine maintenance task requires a special jig or a ladder or a scaffold, that's a red flag. It's a sign of poor design for maintainability, and it increases the time, the complexity, and therefore the risk of that task. You have to design for the reality of human interaction.
This really forces a holistic view. The design isn't finished until you've considered how it will be taken apart and put back together in the real world. This connects perfectly to our final pillar, designing for the full life cycle, not just startup.
Right. Because when an engineering team focuses only on minimizing the upfront purchase price, they're almost guaranteeing long-term financial pain for their company.
The real number that matters is the life cycle cost, the LCC.
The LCC. It's every single penny you will spend on that asset over its entire life, which could be 30 or 40 years. And it breaks down into four main categories.
Okay, what are they?
First is the obvious one, acquisition cost. The capital, the installation, transport,
The sticker price.
the sticker price. Second is ownership cost. This is all your maintenance, preventive, corrective, and any modifications you have to make. Third is operating cost, your energy, your materials. And fourth, and this is the one people often forget, is administration cost.
Administration cost, what falls under that?
It's all the data collection, the record keeping, the documentation, the software licenses you need to manage the asset. If you don't track the asset's history, you can't manage its life cycle cost effectively.
And this is where those abstract design qualities, reliability, and maintainability have a direct and massive financial impact over decades.
It's the key leverage point for a designer. Reliability directly determines how often you have to do repairs, which sets your spares inventory. If you pick an unreliable component because it was cheap,
You're signing up for decades of expensive, unplanned repairs.
you are. And maintainability dictates your training costs, your test equipment costs, your manpower needs, and most importantly, your downtime. Downtime is lost revenue, and it can easily become the single biggest driver of your life cycle cost.
The overall cost of unreliability is just staggering when you look at it this way.
The historical data is genuinely alarming. In the UK, back in the 90s, the total cost of poor quality was estimated to be £150,000 million. Failure costs alone were eating up 4 to 15% of a company's total turnover.
15% of revenue just wasted on things breaking.
Wasted. And here's the crazy part. The amount spent on prevention, on quality engineering, on better design verification, on stopping the failures before they happened, was only about 1% of that total quality cost.
It's a massive strategic imbalance. You're spending all your money cleaning up messes instead of preventing them.
The financial leverage for designing it right the first time is immense. And failure costs aren't just the obvious repair bill. It's the cost of late-stage design changes, of rejecting defective parts from vendors, of scrap, of warranty claims, and all those untracked hours spent fault-finding during commissioning.
So when a design team is looking at two options, a cheap pump and a more expensive, robust one, how do they make the final call? They need a formula that accounts for all of this.
They do, and that formula is based on the net present value, or NPV method. It calculates the total lifetime cost of each option in today's money.
Okay, so let's break down that calculation conceptually for our listener.
Conceptually, the NPV for a component has 4 big blocks. Block 1 is easy. It's the initial installed cost,
What do you pay today?
what you pay today. Block 2 is the present value of all your future planned inspection costs. Block 3 is the present value of all your future maintenance costs, both planned and crucially unplanned corrective maintenance.
And that's where the component's reliability number feeds directly into the financial calculation.
It does. And then there's the final, most important block. Block 4 is the present value of the expected consequences of failure.
So you're multiplying the probability of a catastrophic failure by the massive cost of that failure, the downtime, the environmental cleanup, the potential loss of life, and adding that risk cost into your purchasing decision today.
You are mathematically pricing risk into your component selection, and this framework gives you that critical design insight.
How so?
If a component is in high-use, high-stress service, those maintenance and failure consequence terms, blocks 3 and 4, are going to be huge.
Yeah.
They will easily justify spending more upfront on a super reliable component.
You pay more now to avoid paying much, much more later.
But if the component is in modest, low-stress use, the initial cost block 1 is going to dominate the equation. And in that case, spending a fortune on a gold-plated component you barely use just doesn't make financial sense. It moves the decision from a subjective argument to an actuarial calculation.
We've really covered the full spectrum, from the physics of failure to the psychology of human error, all the way to the long-term economics of design.
We have, and this deep dive really confirms that modern engineering is about numerical accountability. We started with risk quantification, using QRA and SALs to back up our safety decisions with real data. We then showed the absolute fiscal necessity of reliability through the life cycle cost model.
And we learned how to turn our mistakes into real knowledge, using the bathtub curve to understand the failure time and cost-focused Pareto analysis to make sure we're fixing the most important problems first.
And finally, we confronted the critical need to integrate human error into our models with tools like HEART, recognizing that procedures and maintainability design are just as important as the hardware itself. All these methods give you, the engineer, the tools to move beyond opinion and gut feeling.
It changes your role, really. You're not just a technician anymore. You're a strategic partner who can articulate long-term value and risk in the language that management understands. Numbers.
That is your greatest advantage. So we want to leave you with one final provocative thought to chew on, something that builds on everything we've talked about.
Okay, let's hear it.
Given the fact that the majority of serious software errors and design faults actually originate right at the very beginning, at the requirement specification stage, and given that the cost to fix them grows exponentially the longer they're in the system, how much more competitive would your company be if the time and money currently spent on field corrections and warranty work were redirected into implementing formal verification methods right at the absolute earliest stage of every project, even when the scope is still being defined?
A massive upfront investment in getting it right, to avoid a decade of paying to fix it when it's wrong. A lot to think about there. Thank you for joining us for this deep dive. If you found this useful, please hit that like and subscribe button. Let's keep leveling up together.